So often we use length as a surrogate for volume and mass in water balance. Even though the presentations of water balance that I've showed you so far have relied on volume primarily, and I went through a careful explanation of why volume is a good substitute for mass, length is a unit of measurement that we often use when we carry out water balance analyses. So here are a few questions. First, why can we use the dimension of length in water balance analysis when water balance analysis is based on the principle of conservation of mass? Second, why would we use the dimension of length in water balance analyses? And third, how do we use length in water balance analyses? Okay, remember what the basic water balance equation was. First of all, it applies to a control volume, in this case a watershed, and it can be expressed as a rate. So for example, the change in storage with time is equal to the inflow rate minus the outflow rate, which would be the volume per unit time of inflow minus the volume per unit time of outflow. So some of the common processes and units for each component, units that we use for measurements when we obtain measurements for these things. On the left-hand side of this table we see inputs, for example rainfall, and rainfall is always reported in units of length, inches or millimeters for example. Snowfall is the same way at the bottom of the table. Stream or ditch flow as an input is often reported as a rate, volume rate, so we might have a number of cubic units of length per time, and the common unit for length or ditch flow is cubic feet per second. Groundwater recharge is expressed the same way. The outputs, on the other hand, have again similar units. Stream discharge is in length cubed per unit time. Evaporation is often reported in length units or inches or millimeters. Transpiration the same, inches or millimeters. And groundwater discharge out of our control volume would be reported in terms of a volume per unit time. Well, in order to change a volume to a length, we have to divide by an area. So if you look at the units in the very top equation here, volume expressed in length cubed divided by area expressed in length squared yields a length on the right-hand side. Area comes from the surface area of the control volume. It doesn't always work for every kind of water balance analysis, but in this case when we talk about a watershed, we're talking about the watershed being the surface into which inputs go, out of which outputs like evaporation and transpiration go. And we can express the water balance on the surface of the control volume, our watershed, in terms of units of length, if that's the volume if that's the surface area of interest. If we express the original water balance equation as volumes, then our change in storage, which is length cubed, is equal to our inflow in length cubed or volume minus the outflow in length cubed. If we divide the whole equation by the surface area of the control volume, then what we end up with is dividing each one of those terms in the middle by length squared. We end up with our change in storage being expressed as a unit of length, just a single unit of length, as an inch or a millimeter, and the terms on the right-hand side, input and output, also being expressed as units of length. Length is a convenient dimension. First of all, major inputs and outputs, for example precipitation, snowfall, evaporation, and transpiration, are expressed in terms of length, inches or millimeter. This allows us to compare major units or major inputs with outputs, and allows us to directly estimate quantities like evapotranspiration in convenient and relevant units. So instead of expressing evapotranspiration in terms of the number of cubic meters of water that may have evaporated from our control volume or been carried out as a gas from our control volume, we can express it in terms of a length, which is a common way of expressing the evapotranspiration. But here's the thing. This approach requires a conversion, and it's a conversion primarily in the input. We have to be able to express discharge from our control volume as a length. or discharge or recharge into our control volume as a length as well. It's important to remember that discharge, volume per time, is expressed in units of, for example, feet cubed per second. This is commonly abbreviated as CFS, cubic feet per second. In order to express discharge as a length, we have to multiply the discharge rates by the amount of time that's passed to transform the rates to volumes. Here's an example. So essentially we're carrying out a conversion with another piece of information that's not shown here, but in our example it is shown. If we have a volume, or if we have a volume of flow, or flow rate of 10 cubic feet per second, CFS, into a pond, the question is, what volume would be added to the pond after 1 day? Well, essentially this is just a conversion that needs to be carried out, recognizing that our units that are given, 10 cubic feet per second, okay, by multiplying by the number of seconds in a day, we can essentially eliminate the unit of second and express this flow rate, 10 cubic feet per second, in terms of a volume, cubic feet, that we would expect after 1 day's time. So there are 86,400 seconds in a day. That's the conversion factor on the right. If we multiply 10 cubic feet per second times 86,400 seconds in 1 day, and that's the time of interest, we end up with 864,000 feet cubed of water that would have flowed into the pond in 1 day. The next question is this: what if the flow came from a watershed that had a 4.4 square mile area? Well, this is going to become the bottom of our equation when we divide volume by area. This will become the area that we divide the volume by to estimate the total number of inches that came from the watershed in 1 day. This is an equivalence. It's the equivalent number of inches based on the volume of flow. In this case, our watershed area is 4.4 miles squared. We need to convert that to feet squared in order to carry out the first stage in the division. So we multiply that times our conversion factor, which is that 1 mile is equal to 5,280 feet, but it's square miles, so we have to square the conversion factor, which means we end up with 122,664,960 feet squared in our watershed area. This brings us to our last step, which is to change the volume, flow volume, to a length. And our equation, our basic equation, is that volume divided by area is equal to length. In this case, we take our volume, 864,000 cubic feet of water. We divide it by our surface area of our watershed, 122,664,960 feet squared. And we come up with then a number of feet of water that represents, that flow represents as output from our watershed. So in this case then, it's 7 times 10 to the minus 3 feet. But we're not quite done, and I'll leave the last calculation to you. We really need to express that in terms of inches, because often when we talk about, again, flow out of a watershed or evaporation, it's handy to be able to compare the number of inches of flow, and this is assuming that the entire watershed acts as a single unit, which it doesn't. But we need to express that in terms of inches. So let's go over these questions again. Why can we use the dimension of length in the water balance analysis? We can use it because we can divide the dimension of volume by a constant, which is our watershed area, to end up with a unit of length that carries forward into our water balance analysis. So it becomes a legitimate use of the dimension length. And why would we use this? Well, we use it primarily because some of our major inputs, precipitation, snowfall, and our major outputs, evaporation and transpiration, are expressed in terms of length rather than in terms of volume. It's also just a handy and fairly compact quantity to use to carry out our water balance analyses. It's a little bit more comprehensible to understand that we had, for example, a very small number of inches of water that left a watershed than a number of cubic feet. Cubic feet really people have a very difficult time understanding what a number of cubic feet represents in terms of output from a watershed. And how do we use length and water balance analyses? Well, we're given some dimensions in the basic measurements that we get from weather stations. For example, precipitation and snowfall. However, we have to do conversions in order to take other measurements, for example, the number of cubic feet per second of flow in a stream. We have to convert those in order to put those on an equivalent basis so that we can carry out our water balance analysis in terms of units of length.